Hello? 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 Hello?
Hello! We're going to talk about cells that are far apart communication. We just talked about the cells that are how they're stuck together and how they can send signals through gap junctions and plasmodesmata and how they're stuck together with all those kind of things. But how do they communicate if they're not right next to each other? We call it cell signaling. So one signal has to be sent from one cell and received by another. Duh. So,
Oh, great.
yeah, it is kind of great, right? So this chemical messenger, a protein, think of it like a hormone, right? Binds to a receptor on the target cell. This is a target, right? And it would be a receptor, right? That protein that sticks out, maybe a glycoprotein, something like that. And then the guy sent that binds is called a ligand. I say ligand. And so it would be receptor and ligand interaction, and then that transduces a signal down. Sometimes it causes gene regulation, sometimes it causes genes to turn on, genes to turn off, gene regulation, duh. Or, sends second messengers in or through to communicate, do stuff. Just that's in general. Receptors, specific for the exact signal. So not just one receptor, there's a receptor for every single ligand. And this is what we can block. Sometimes we do that with drugs to stop that signal from going from one cell to another. What happens when it's actually received, what I was talking about, the receptor can change conformation, right? If it's a protein and it interacts with something else, it might change shape, right? Because of the chemistry, might make it change its shape. The shape determines function. It might now do something, might do something else, or it might transduce a signal through into the cell. So it's converted into some other kind of signal in code, so it can be recognized down the line. I know that sounds super generic, and I know cell bio will give you so much more information than this if you get there, but hang in there, just the basics. So, for example, receptor tyrosine kinase, this is the receptor, right? The signal would be the ligand, and the signal arrives and binds to the receptor. Oh. And there we go, it changes shape. So similar to like an enzyme and its substrate changes shape, same idea. Proteins can change shape when they interact, right? There are groups, hydrophobic, hydrophilic, acid, basic, all that stuff, right? The chemical interactions with whatever that ligand is, another protein that has hydrophobic, hydrophilic, blah, blah, blah. That causes conformational change, which causes a change down here. It might become phosphorylated. We steal a phosphate off of ATP and make ADP, right? Inactivate some kind of protein because we stole a phosphate from it, right? We might take another phosphate and put it on this inactive protein, right? That might be another inactive protein that we add a phosphate to. Who knows? There might be another one, and so on, and so on, and so on, and activate it all the way down until it binds to DNA and causes some change, right? Or does something else. And so that's all we're going to say about that. You're going to get signal transduction up the wazoo in Bio 380, so hang on for that. But if we want to talk about some cool stuff in bacteria, right, we talked about unicellular organisms, right, don't stick together, but sometimes they do. Remember I said foreshadowing? Ooh, yeah. So they live together and they can communicate with one another, and they call that quorum sensing. That's just the name. A quorum is when you have enough in a group to do something. So like if you're at faculty meeting, you need, at 2/3 or 3/4 of all faculty to be there to make some vote count. You have to have a quorum. So bacteria release, again, signaling molecules, same idea. They would secrete them out of their individual little cell. Ooh, there I am, I came out. And then the response of another guy. Who knows? He might get sad. He might get happy, right? They don't really feel stuff, right? I know, I lied.
Oh, great.
Yeah, sorry. But, right, you get what I mean. I hope. So, yeast cells can alter growth, right? They're growing on this red side here. Well, I guess I could do it red, right? And that's signals from their environment. A slime mold, ooh, it's a mold. What is a mold? It's a fungus, right? They aggregate in response to sending a quorum. So the cells migrate in towards a central point to all get together. And that's from signals in the environment coming from cells secreting them. What about bioluminescence? Ooh, we emit light. Secretion, again, there's our favorite word. Allow bacteria to attack us host. Ooh. And then the most fun one is the secretion of a biofilm, which is a hard polysaccharide-rich substance that they secrete out and allows them to stick to surfaces. Right? As a big group. And why is that cool or why is that gross? Because let's look. Ew! That's what bacteria do to your teeth, right? They eat away at the enamel, and all this plaque is a bacterial biofilm. So brush your teeth. Go to the dentist. Get a good cleaning. I know Health Services has some dental cleaning. So if you haven't had your teeth cleaned in a while, think about what might happen. Yikes. And then there's a picture of the actual bacteria sitting on your teeth, right? Doesn't that look really good? Yay. I love that. And then, ew, I know. It's another, this is actually, I think it's, actually, I don't know what it is, but it's making, like, right? This is the biofilm, and yeah, it's disgusting. And here we go. This is what it would actually look like if we're taking, like our teeth would be down here. This is that polysaccharide. What's a polysaccharide, my friends? Sugars, carbs. Oh, carbs. Oh, and then the bacterial cells living on top, and they're all stuck, right, to your tooth that way. Otherwise, your teeth are kind of slippery. Ow. And that's it. So that was nice and quick. So what do you think of that?
Oh, great.
Yeah, it's already done. So wahoo, let's be done.